Welcome back to the deep dive. Um, this time we're going deep into the history of quantum gravity research. We've got a great paper to guide us. The Quantum Theory of Gravitation, Effective Field Theories, and Strings, Yesterday and Today, by Roche and Van Riet.
It's a dense one, but really comprehensive.
Yeah, and as everyone knows, reconciling Einstein's general relativity with the quantum world has been a massive challenge in physics. What's really interesting is how that pursuit has changed how we view, well, not just gravity, but like the whole standard model.
Totally. An effective field theory, or EFT, that's really key to all this.
Right.
And the paper, it really digs into how thinking on this has evolved.
Yeah.
Starting from those early attempts to quantize gravity.
Way back.
Yeah.
Early 20th century stuff.
All the way to string theory and the swampland program, the modern implications.
So let's start, like you said, early 20th century. Everyone's just figuring out quantum mechanics. And the paper talks about how physicists like Rosenfeld and Bronstein, they were drawing an analogy between gravity and electromagnetism.
Yeah, hoping to, figure out how to quantize gravity that way.
Makes
And
sense.
it turned out to be really tricky.
So what did their work actually show?
Well, they realized that the usual methods of quantum field theory, the ones that work so well with electromagnetism, they just didn't quite fit when you tried to apply them to gravity. One of the main things they found was that when you calculate gravitational self-energy, these infinities pop up.
Infinities.
Yeah.
Those are always fun.
And this problem, it actually stuck around for decades.
So it wasn't just a math quirk. These infinities were a sign of a real problem.
Exactly. They showed that there was this fundamental clash between general relativity and quantum mechanics, especially when you get to really high energies or really tiny distances, where quantum effects become really important. And the paper actually talks about how Rosenfeld in 1930, he looked at the gravitational self-energy of light, which was super groundbreaking at the time.
That's blown some minds.
Yeah, but not everyone was convinced.
Oh, really?
Yeah, the paper even mentions Oppenheimer. He kind of dismissed this whole thing as, highly academic.
So it wasn't exactly a hot research topic.
Not at the time, no. But some people kept working on it, on quantizing gravity. And that brings us to the Jablona Conference.
And when was this?
1962.
Okay.
Really important event. You had people like Feynman there, DeWitt, Uchiyama.
Big names.
Yeah, and they were presenting all these new ways to deal with those infinities. They started talking about ghosts and higher derivative terms.
Okay, those sound a little out there. Can you break those down a bit?
Sure. So ghosts in quantum field theory, they're kind of like fake particles. You introduce them to make the math work out. They appear in theories that have certain symmetries, like the gauge symmetry you see in electromagnetism and general relativity.
Right.
Yeah.
And what about those higher derivative terms?
So in Einstein's general relativity, you have these equations. They describe gravity, and they involve derivatives of this thing called the metric tensor. It basically describes the geometry of space-time.
Okay.
And usually you only have derivatives up to second order. But in higher derivative theories, well, you add terms with, third, fourth, even higher order derivatives.
So Feynman, DeWitt, and Uchiyama, they were basically tinkering with the equations of general relativity.
Yeah, pretty much.
Trying to get rid of those infinities.
Exactly. They were testing the waters, seeing if adding these extra terms would make the theory behave better when you quantized it.
Interesting.
DeWitt, he even suggested that people should look at radiative corrections. Those are the changes that happen because of quantum fluctuations, and how they affect the Schwarzschild solution, which is the metric that describes the gravitational field around a spherical mass, non-rotating, that is.
So even back then, they were thinking about how the quantum world might actually change the fabric of space-time?
Yeah, they were onto something. And that actually led to people trying to calculate quantum corrections to, Newton's law of universal gravitation.
Wow, so from light to Newton, big jump.
Yeah, and the paper talks about this guy, Iwasaki. He had this semi-classical approach in 1971.
Semi-classical?
Yeah, it was like a bridge between classical and quantum gravity, a clever way to try and connect the two.
So he was trying to calculate how quantum mechanics might tweak Newton's law.
Yeah.
Interesting.
And then you have Duff. He came along in 73 and 74, and he used these new techniques, renormalization, to try and calculate those quantum corrections to the Schwarzschild solution.
So building on Iwasaki's work.
In a way, yeah. But there's a funny story about Duff's work. It was actually sparked by a bet between Salam, Penrose, and Wheeler.
A bet.
Yeah, like a wager. It shows how much skepticism there was about these quantum gravity calculations back then. Most people thought it was just theoretical, not something you could actually measure.
It does seem pretty far out, thinking that quantum mechanics would have any real effect on gravity, like on a large scale.
It does, but as we'll see, these seemingly academic calculations, they ended up changing how we think about gravity in a huge way.
Okay, I'm intrigued.
And a big part of that shift came from 't Hooft and Veltman. They proved in '74 that when you couple gravity with matter, it's actually not renormalizable.
Not renormalizable.
Okay.
So that means...
That means you can't get rid of those infinities.
Yeah.
And renormalizability, that used to be like, the gold standard for a good physical theory.
So this is a big deal.
Huge. And Goroff and Sagnati, they later confirmed this for pure gravity in '86. So physicists were forced to rethink how they were approaching quantum gravity.
Okay, so what did they do?
Well, one path they explored was higher derivative theories of gravity, and those have their own, really interesting history.
Okay, let's hear it.
So it all goes back to Waddell in 1918. He was trying to unify gravity and electromagnetism, right?
Right.
And he came up with this Lagrangian that had a term with the square of the Riemann curvature tensor. It basically describes the curvature of space-time.
Okay.
And that's how these higher derivative terms got into the picture. They weren't just random additions. They came from this deep desire to unify the fundamental forces.
I see. So trying to unify things led to these new terms.
Yeah, and it doesn't stop there. In '66, Pechler and Sexel, they connected these higher derivative theories to something called effective Lagrangians. This idea would later be super important for developing EFT.
So pieces starting to fall into place.
Yeah. And then Sakharov in '67, he built on these ideas and said that these higher derivative terms could actually be quantum corrections to Einstein's theory, especially in cosmology.
So all these different threads, unification, renormalization, cosmology, they're all pointing towards these higher derivative theories.
Exactly. It's like they were hinting at something deeper. And then you have Stell. In '77 and '78, he showed that some of these higher derivative theories, they could actually be renormalizable, which was a huge breakthrough. It seems like maybe these theories held the key to quantum gravity.
So did they? Was that the answer everyone was looking for?
Well, not quite. Stell's work also showed that these theories, when you take them as a full description of quantum gravity, they make some pretty weird predictions.
Weird how?
Like you get particles with negative energy, things like that.
That doesn't sound good.
Yeah, it raises questions about whether these theories are actually the fundamental picture. But those problems, they wouldn't be deal breakers when you look at things through the lens of EFT.
EFT.
Yeah, effective field theory. That's where we start to see a real revolution in how we understand gravity. And that's a story for next time.
Okay, cliffhanger. I guess we'll have to wait for the next deep dive. Okay, so last time, things got pretty complex with all those higher derivative theories. But you mentioned this thing called EFT, effective field theory. What is that exactly?
Right. So EFT, it's basically a way to describe physics at a certain energy scale without needing to know the full underlying theory.
Okay, can you give an example?
Sure. Think about Newtonian mechanics. We use it all the time to describe how planets move.
Right.
But we know that when things get really fast or gravity's super strong, you need Einstein's general relativity. That gives you a more accurate picture.
So it's like Newtonian mechanics is an approximation.
Exactly. And that's kind of the idea behind EFT. You focus on what's relevant at the energies you're working with.
So it's not that those simpler theories are wrong.
Right.
They're just effective descriptions. They work within a certain range.
Exactly. And it was Weinberg who really saw the power of this. He kind of changed how we think about fundamental physics.
Weinberg.
Like?
The Steven Weinberg. The standard model guy.
Yeah, the one and only.
Wow. So he did more than just particle physics.
Oh, yeah. He had his hand in a lot of things, including gravity. He actually challenged this idea that a theory had to be renormalizable to be considered valid.
So before Weinberg, if you couldn't get rid of those infinities,
Right. If it wasn't renormalizable.
people just thought, okay, this theory's not complete.
Pretty much. But Weinberg's work with EFT, it showed that non-renormalizable theories, they can still make good predictions.
Within certain limits, right?
Yeah, within a certain energy range. And the paper mentions his 1976 lectures in Arese, Italy. Those were really important for shifting this thinking.
So what did he say in those lectures?
Well, he built on this work by Kenneth Wilson on the renormalization group, and he argued that these non-renormalizable theories, they could be just as valid, just as predictive as the renormalizable ones, at least, within a certain range of energies.
So we don't need a single theory that explains everything at all energies. We can have different theories that work in different domains.
Exactly. Focus on the degrees of freedom that matter at the scales you can actually access. Don't worry so much about finding one ultimate theory of everything.
That's kind of a relief, actually.
Yeah, it takes some pressure off. And this had big implications for how we understand gravity.
How so?
Well, Weinberg realized that even general relativity could be seen as an effective field theory.
Wait, so general relativity, the theory that describes, like, the entire universe.
Yeah, that one.
That's just an approximation, too.
It could be, yeah. It might just be a low-energy version of something more fundamental.
Mind blown.
It is a pretty wild thought. His 1979 paper on EFTs, it didn't actually mention gravity specifically, but you can see the seeds of the idea there.
So he is already thinking about it.
Yeah, definitely.
Yeah.
And then, in his 1980 Nobel lecture, he came right out and said it. General relativity is an EFT.
So even as he was getting the Nobel Prize for his work on the Standard Model,
Right.
he was already laying the groundwork for a new way of thinking about gravity. It's pretty impressive.
Yeah, Weinberg was a real visionary. He saw the connections between different areas of physics. He understood that the Standard Model, general relativity, they were probably just pieces of a bigger puzzle.
Okay, so Weinberg lays out this new framework, this idea of general relativity as an EFT. What happens next?
Well, not everyone was immediately on board. As you can imagine, it takes time for new ideas to, take hold. The paper mentions some of the early work that followed Weinberg's lead. Like Adler in the early 80s, he built on Sakharov's ideas and started exploring how the gravitational action could be understood as, an effective description.
Effective meaning.
Meaning it comes from some deeper, more fundamental theory, something we don't fully understand yet.
Okay, so they were taking this effective gravitational action seriously.
Yeah, but there was still this hesitation to, completely let go of renormalizability. A lot of people, including Adler, they thought there had to be some underlying theory, probably a renormalizable one, that gave rise to this effective action.
So giving up renormalizability was tough, even with all this new evidence.
Yeah, it was a big shift. But then something really interesting happened. People realized that they could actually calculate quantum corrections to the Newtonian potential.
Those tiny corrections we talked about earlier?
Yeah.
The ones that seemed impossible to measure.
Yeah, those. Turns out you can calculate them.
How?
Well, Donahue, in the early 80s, he figured out that if you carefully consider the low energy degrees of freedom and you use the framework of EFT, you can actually compute these finite quantum corrections.
So EFT gives you a way to do these calculations that were impossible before.
Exactly.
But if they're so small, why even bother?
Well, Donahue himself, he thought it was just an academic exercise. He didn't even publish his results right away. He didn't think they were practically important.
So why are we talking about them now?
Because things get really interesting when you bring string theory into the picture. That's where the bottom-up approach, where you start with general relativity and add quantum corrections, meets the top-down perspective of string theory.
String theory. Okay, here we go. The deep end of the pool.
Right into it.
String theory. So just a reminder, well, that's the one where the basic building blocks of the universe aren't particles, but like tiny vibrating strings, right?
Right. And those strings, they vibrate in different ways, and that's how you get all the different particles and forces, including the graviton. That's the hypothetical particle that carries the force of gravity.
Okay, so string theory, it tries to bring together general relativity and quantum mechanics. And how does this all connect to those higher derivative terms we were talking about?
Well, one of the cool things about string theory is that it naturally includes those higher derivative terms, the ones that caused all those problems when people tried to renormalize general relativity.
You mean the ones that Stell showed could lead to renormalizability, but also like weird stuff like particles with negative energy?
Exactly. But in string theory, those terms, they just kind of pop out naturally from the way those strings interact. They're not just added in by hand. They come from the underlying structure of the theory. The paper mentions this guy, de Alwis, back in '86. He used those powerful renormalization group equations to show that those higher derivative terms could actually emerge as quantum corrections to the Einstein-Hilbert action.
The Einstein-Hilbert action, that's like the foundation of general relativity, right?
Yeah.
So string theory is saying that these corrections, they're not just some arbitrary fix, they're like a natural consequence of the way gravity works at a deeper level.
That's the idea.
Wow. So string theory, it kind of justifies that bottom-up approach we were talking about,
Yeah.
where you start with general relativity and add in those quantum corrections.
Right. It's like those higher derivative terms were hinting at string theory all along.
It's like we were seeing the shadows of a higher dimensional world.
Yeah, that's a good way to put it. And this idea that string theory could be the UV completion of general relativity, meaning it solves the problems at high energies, it really took off in the late 80s and early 90s. A lot of research started focusing on string scattering amplitudes. The paper talks about Amati, Cifaloni, and Veneziano. Back in '87, they were looking at scattering processes in superstring theory.
So basically, they were trying to understand how these strings interact with each other.
Yeah, and what those interactions tell us about gravity at the quantum level.
Makes sense. What did they find?
Well, they made a pretty remarkable discovery. They found a quantum correction to the Schwarzschild metric.
Hold on, the Schwarzschild metric, that describes the gravitational field around a black hole, right?
Yeah.
Or you're saying even that, like, the geometry of space-time itself, it's affected by these quantum fluctuations.
It seems that way, yeah.
Wow.
And then you have Iengo and his collaborators. They went even deeper into these scattering amplitudes, and they found both classical and quantum corrections to the Newtonian potential. Really impressive calculations. They show how powerful string theory can be, how it can make specific predictions about quantum gravity.
So we've got these two approaches, right? The bottom-up with Donahue and those calculations, and the top-down from string theory. And they're both pointing to these quantum corrections to gravity.
Exactly. It's like they're two sides of the same coin.
But both approaches, they still have their problems, right?
Yeah, of course. Like we said, Donahue, he initially thought his calculations were just like a theoretical curiosity, too small to actually measure. And string theory, well, it's had trouble making concrete, testable predictions about our four-dimensional world.
Okay, so where do we go from here? Where does this all leave us in our quest to understand quantum gravity?
That's the million-dollar question. The paper talks about two key ideas that are shaping our current understanding: moduli stabilization and the Swampland program.
Okay, those sound pretty complicated.
They are, but really important. So moduli stabilization, it's all about dealing with those extra dimensions that string theory predicts, trying to figure out how to make their size and shape fixed so we end up with a stable four-dimensional universe.
Sounds tricky.
It is. It's like trying to fold a piece of paper into a very specific origami shape and making sure it doesn't like unfold or collapse in weird ways.
Okay, I can kind of picture that. And what about the Swampland program?
So the Swampland program, it's more like a set of rules. It asks, what kinds of effective field theories are actually allowed if you want them to fit with the quantum theory of gravity? Are there like fundamental limits, maybe coming from string theory, that tell us which EFTs are actually possible?
So it's like trying to figure out the grammar of the universe.
Yeah, that's a good analogy.
We're trying to find the rules that tell us which theories make sense and which ones are just, like, nonsense.
Exactly. And the Swampland program, it's shifted the focus away from trying to build specific string theory models that perfectly reproduce, like the standard model and general relativity. Instead, it's about finding general patterns and principles that govern all those possible EFTs.
So it's less about building specific models and more about understanding the big picture, the underlying structure of things.
Right. And this shift in perspective, it's led to some fascinating ideas, like the weak gravity conjecture, which says that gravity has to be the weakest force in any consistent quantum theory of gravity.
That makes sense, intuitively. But I bet it has a lot of implications.
It does. It limits what kinds of EFTs are allowed. And there are other conjectures, like the de Sitter conjecture and the ADS distance conjecture. They have big implications for things like dark energy and the scale where we might see new physics.
So even though we don't have a complete theory of quantum gravity yet, these Swampland conjectures, they're giving us some clues about how the universe might be structured at a fundamental level.
They are. They're pointing to these deep connections between gravity, quantum mechanics, and space-time itself.
Well, this has been quite a journey. From those early attempts to quantize gravity all the way to string theory and the Swampland, it's clear that trying to understand quantum gravity has really changed how we think about the universe.
It definitely has. And even though there are still a lot of mysteries out there, the things we've learned along the way, they've opened up whole new ways of thinking about physics.
It's amazing to see how all these different ideas, like higher derivative theories, effective field theory, and string theory, they all connect and give us different pieces of the puzzle. So for everyone listening, as we keep exploring the quantum world, Who knows what other strange and surprising connections we'll find? What new ideas will we come up with? This journey of discovery, it's definitely not over yet. There's still so much more to learn about the universe.